So today we're going to talk about the toxicity of structural erosion and how to fight it. And first we're going to define what is structural erosion and how we can measure it. And then we can talk about measures, how to limit it or even get rid of it. Here's a nice example of something that happened to an open source project, Apache Cassandra, which is a pretty popular Java open source project. So what we see here is a package dependency graph from Apache Cassandra. It's a pretty big cycle group of about 50 Java packages, and they're all in a big cycle. So everything is connected to everything. That's basically almost all of Cassandra, all the packages of Cassandra in a big cycle group. And you can measure that actually. There are two metrics here, which I mentioned on the bottom. Maintainability level is at 9% of a possible 100%, which is pretty bad. And propagation cost is at 62%. That means every time I touch something in Apache Cassandra, it might affect directly or indirectly 62% of Cassandra. So that, of course, makes it really hard not to break something if you touch something. So it is not very well structured. That doesn't mean the software is bad. It has a pretty good test suite coming with it, and it's a pretty successful project, but it definitely means that the code is hard to understand, it's hard to test, and close to impossible to modularize because now everything is so tightly packed that they optimized the architecture diagram to a single box labeled Apache Cassandra. So what is structural erosion? I would say we can see over time that the code deviates more and more from any architectural blueprint, if there was one in the first place, because many projects actually don't have real architectures. They have some ideas in the head of some developers how code should be structured, but it's not formalized and even less enforceable. And when we do software assessments, and I did quite a bit of them, I can tell you that about 80 to 90% of all projects are going to end up as a big ball of mud, looking pretty similar to that dependency graph of Apache Cassandra. So one typical symptom you're going to see is that cycle groups are growing bigger and bigger. I call it code cancer. And therefore the code becomes harder to test and to maintain. Also, people spend a lot of time reading code and very little time writing code. And the probability of regression bug, of course, here, the more tightly coupled your code is, the higher is the chance that something completely unrelated breaks if you do changes to your code. To introduce some terminology here, what is a cycle group? This is a dependency graph, so the little circles are Java files or C# files or whatever you have as compilation units, and the arrows are dependencies between them. And in this graph, we can see two cycle groups, red and gray. They're definitely cyclical dependencies. The white nodes are not part of any cyclical dependency. So, and the cycle groups are a good indicator to measure structural erosion. Because what we know, the more structural erosion you have, the bigger those cycle groups become. So why are they bad? Why are cycle groups a bad thing? First of all, they make the code harder to understand because they couple things together. Testing becomes harder because everything that's in a cycle group must be tested together. You can't test anything in a cycle group in isolation because they're all depending on each other in a circular way. Modularization becomes more difficult. So that's the thing. Many people are jumping now on the microservices train, and they try to break up their big monoliths just to find out that at the end they have a big ball of mud on the network level and not really helping their cause. It's not making things simpler, and that was the initial goal of creating microservices. Coupling increases, of course, and for my recommendation, I always say that you should try to avoid cycle groups with more than 5 elements. So cycle groups between compilation units should not have more than 5 elements, and namespace or package cycles, in my opinion, should be completely avoided. So in my company, the build actually breaks if somebody tries to introduce a package cycle. So our tools on our graphs are completely cycle-free when it comes to package cycles. And then the good news is all cycles can be broken. And for example, dependency inversion principle, according to Robert C. Martin. And then we talk a lot about this in our training courses because that's an important skill, and too few developers actually learn that. And I would hope that you add this to your course material because it's just an important skill how to get rid of cyclical dependencies. Many developers actually don't know that. So we can actually see that in open source projects. I did a little digging in Apache Cassandra and compared version 2, 3, and 4. And in version 2, we had about 450 Java files in a single cycle group. In version 3, that two grew to more double the size. It had at the end more than 900 Java files in a single cycle group. And in version 4, this cycle group increased to 1,304 elements. It's really a big mess. Everything is connected to everything. And in version 4, we also, the two more metastasized, we added two more cycle groups with 143 and 31 Java files. So everything is very tightly coupled. And you have to put this into relation that version 4 has 1,981 Java files. So basically, you could say that 3/4 of all Java files are in one of those three cycle groups. You can also measure that with the metric relative cyclicity. It turns out to be 66.2%. 100% would be the worst, where you really have one big cycle with 1,981 files. It's not that bad, but pretty close to it. So how do we measure structural erosion? I think a very good first indicator is looking at the biggest cycle group. So if you have a cycle group with hundreds of elements, you already know you're in trouble. That's if I do assessment, that's one of the first things I look at. How is the cyclicity of that system? How big are the cycle groups? How well modularized and verticalized is the code? And there are several metrics good to measure it. We talked about relative cyclicity, then we have propagation cost, maintainability level, and structural depth index. The last two metrics are metrics that have been developed by my company. If you are interested in the details about maintainability level, there's a blog article on blog.hellotomorrow.com that explains that metric pretty well. It is basically a little bit based on the idea of decoupling level. I talked about that yesterday. That is protected by a patent, so I sort of built something similar that is about as good as this particular metric. Structural depth index is also interesting because it allows you to estimate how much time you would need to break up a cycle group. So basically, we run a graph algorithm over the cycle and try to find a minimal breakup set. And then for each connection that needs to be cut, we add 10 points. And then each of those connections can have several parser dependencies. So for each parser dependency, we add another point. So that, of course, structural depth index is a little bit more precise than just looking at cyclicity because it tells you also how difficult would it be to break up the cycles. Now let's have a quick look at Cassandra with SonarGraph. What you see here is our exploration view. We're working with those arcs. The arcs are going counterclockwise, so everything in the left half of the circle is going top down and everything on the right half of the circle is going bottom up. SonarGraph tries to minimize upgoing dependencies. So if you didn't have any package cycles in Cassandra, you wouldn't see anything on the right side and you would pretty much see the layering in the order of the packages. But of course, it's very cyclical, so we don't have that luxury here. So that's actually the graph that I was showing here from Cassandra. And it doesn't look very pretty. Now, if you look at the system metrics, you can see pretty quickly what happens, and the diffs are between version 3 and version 4. Average component dependency is also an interesting metric. It tells us if we change a random file, how many other files would directly or indirectly depend on it. And here the number is 1426. So every time I change a Java file, it might directly or indirectly affect these many other Java files, which is bad news. So that number should be below 100 or in the low 100s, that before a system of that size, but this is definitely way too big. You can see it here. And the cool thing about those metrics, if you actually measure them on a regular basis, you get an early warning indicator and can do something to address the problem before it becomes too hard to fix. With Cassandra, we're at a point right now where it's almost too hard. Now, if we look at the cycle groups, just for fun, now, should we visualize it? It's not gonna be very interesting, but just for fun, I think we can just try it once. It takes a little time, so you get this big ellipsis with dependencies, and of course you don't see anything. That's not a useful visualization. I can switch to spring embedder layout, it becomes slightly more useful, at least because now I can see with those colors of the Java files, I can see the different parents. So different colors means different parent packages. But it's, of course, you don't see much. It's more interesting to look at a little bit of a smaller cycle group, for example, this one here. There we can still see a little bit. And this is also interesting to visualize in the exploration view. Because as I mentioned before, Sonograph tries to minimize the outgoing dependencies, but here we see we have a lot of things going up on the right side still. So this will be hard to disentangle. And we can confirm that I have what we call a cycle breakup view. This is down here, and here I can compute the breakup set. And we tell us we have 31 cyclical nodes, 108 edges in the graph, and we would have to remove 22 of those edges. Would be 71 parser dependencies, 71 lines of code that might be affected. And here we get a list of all the dependencies we need to cut. The color scheme here, you see those blue lines and green lines. The blue lines basically are direct feedback loops between two Java files, and the green lines are more complex feedback loops with more than two hops, more than two elements involved. And I can just highlight all of them if I wanted to. And here we can see which one we would have to remove. And they're basically mostly blue lines, of course, but some of the green lines too. And it also, there's no low-hanging fruit. Sometimes you get lucky, you can just remove one dependency and it will fall apart into smaller groups, but we're not that lucky in that case. Okay, so that's just a very quick idea what you can do to measure and visualize this kind of stuff. Now, how could we fight it? First of all, as a rule, as a general rule, I always recommend avoid package or namespace cycles. Break the build if that happens. And you can even do that with our free tool, Sonograph Explorer. Sonograph Explorer can also be run in the build and can be configured to break the build if there's a package cycle. I also highly recommend to limit compilation unit cycles to maximum 5 elements. Even better, avoid them totally. Certain patterns, of course. Certain design patterns sometimes. Certain design patterns imply certain cyclical dependencies. For example, the visitor pattern involves a cycle, but we improved the visitor pattern a little bit in our company, and we have a cycle-free version of it by now. And then, of course, it's always good to limit complexity and size of source files. Don't have those God classes which control everything. And last but not least, have an enforceable architectural model. And that's where our architecture DSL, domain-specific language, comes into the game. That's a tiny little example here. We have on the right side a little architecture diagram with some layers, and on the left side the equivalence in our architecture DSL. And we can see that we basically the boxes in the architecture diagram are the artifacts. The include statement tells you what is in the box, and then the connect statements and the stereotypes of the artifacts tell you what they can use. For example, the stereotype strict means I can just access the next layer beneath me, in contrast to relax, which would allow me to access all layers beneath me. So strict layering means I can just go one layer down. Business is a little exception. It can go to service, but it can also go to persistence because it has that extra connect statement here. Services, again, is strict and can access persistence. So just to give you an idea how that DSL looks like, that's actually a pretty efficient way to describe an architecture, and we have many customers using that for a long time now. To give you an idea, we have one logistics company in Germany using it for more than 10 years, and they have about 3 million lines of code and need about 800 lines of DSL to have a complete, very fine-grained description of their architecture. And they can break the build now. As soon as somebody would go from the database layer, from the persistence layer to the presentation layer, that would break the build.